In this particular example, what we're going to do is we're going to look at calculating the pH of an acid-base titration at the equivalence point, specifically at the equivalence point. So let's take a look at this one. I'm going to bring up the example. So in this one, a chemist titrates 140.0 milliliters of a 0.5782 molar butanoic acid solution. Butanoic acid is a weak acid with 0.1698 molar KOH, which is a strong base at 25 degrees C. Calculate the pH of the equivalence, and the pKa of butanoic acid is 4.82. Round your answer to 2 decimal places. Okay. So this one will involve quite a few steps. So make sure you get all the information down and then take a look, and we're going to organize that information and then do a little bit of reasoning for these calculations. Okay. So let me bring this up. Our first step in any of these titration problems is to write the equation. So butanoic acid, that's its formula. It's going to react with KOH. If you're using a hydroxide base, you can just do the double replacement. So the H plus from the acid is going to go with the OH minus from the base to give you water. And then your metal is going to connect with the non-metal to give your salt. Okay, next step is to go through your initial calculations of moles or millimoles and all of that kind of good information. So here's what we have. We have 140.0. Actually, let me go ahead and write it up here. We have 140 milliliters of the butanoic acid. And we also know it's 0.57, 82 molar. So I'm going to write it right there. From that, we can calculate the millimoles. We just multiply them together. 140 times 0.5782, and you get 80.948. Now the KOH is a little different. For the KOH, they only give us the volume. They tell, I'm sorry, the molarity. They only tell us that it's 0.1698 moles per liter. They don't tell us what the volume of that solution is. So how do we find that volume? Well, let's use logic. This is at the equivalence point. If it's at the equivalence point, the moles of the acid are equal to the moles of the base. They're equal to each other. So that for this particular problem, that would be 80.948 millimoles. So that's the number we have. So what that allows us to do is to say that the volume times the molarity is equal to 80.948 millimoles. So I'll just put a V in there. And we're going to calculate the V. The volume of the potassium hydroxide would be the millimoles of the potassium hydroxide divided by the molarity. Moles cancel and you get milli over 1 over liters, which is milliliters. So 80.948 divided by 0.1698, 476. 0.73 meters. So that's one way that this problem differs from the previous titration problems. I'm boxing off a couple of important numbers. 3 actually important numbers. The difference here is that since it's at the equivalence point, we know the number of millimoles of the base because we calculated it from the acid. They have to be equal to each other. If it's not at the equivalence point, we can't use that assumption. But if it is at the equivalence point, we can. Okay. So now, from that information, I'm going to write out that the total volume of the solution at the equivalence point would be the initial volume, 140 milliliters, plus the amount of KOH solution that we added, 476.73. So if we add those together, you get 616.73 milliliters. Okay, so there's the volume of the mixture together at the equivalence point. Now let's go through our stoichiometry. The stoichiometry says that we're going to start with 80.948 millimoles of each. We're not going to worry about water. This is 0. Okay. What happens? They react. Now, since they're equal to each other, stoichiometric amounts, we call that, they're going to go down to 0. This is millimole, by the way. So these are both 0. Again, we don't worry about the water, but this is going to go up by 80.948 millimoles. And here's the key to this problem. Since we don't have any acid or base left over, we have to look at the products to determine what will happen for the pH. They're the only thing left. And here we have a weak base. Now, how do I know that's a weak base? Because it is the conjugate base of a weak acid, right? The conjugate base of a weak acid is a weak base. So we have a weak base. So this is a weak base problem. The calculation of the pH will be based on how much of that weak base is put into the solution. Okay, so what I'm going to do is calculate the concentration of this weak base. Now notice I'm not putting the potassium in the formula because that's part of the salt, but potassium is the conjugate acid of a strong base, so it has no effect on acidity. It's the C3H7CO2-, which we would call butanoate. That is the conjugate base of the weak acid. That's what's going to affect the pH. So we need to know the millimoles, and we need to know the number of milliliters in order to find its molarity. So we figured out this is the number of millimoles produced. And then the volume, see how I calculated that volume? I did it for a reason. This is where we're going to use it. Okay, so 80.948 divided by 616.73, 0.1313. Notice how I said, hey, that's molarity because the millis cancel, you have moles per liter. Okay. Now we're going to treat this as a weak base problem. But we have to be very careful because they didn't give us anything about the Kb or the pKb. They just gave us the Ka of butanoic acid. Okay, so here's what I'm going to do. The pKa of butanoic acid is 4.82. Okay, so there's a couple different ways you can do this. One is to say, look, pKb plus pKa equals 14. So that means your pKb would be the 14 minus the pKa, which would be 14 minus your 4.82. And that's, was that 9.18, I guess? Let me see if that works out. 14 minus 4.82, 9.18. And then Kb would just be 10 to the minus pKb. So 10 to the minus 9.18. Okay, so I'm going to make that a 10 to the x of minus 9.18. And you get 6.607 times 10 to the minus 10. So there's your KB. So I'm going to write that KB down. I'm going to write my initial concentration down. Because if we want to calculate the pH of the weak base like we did in chapter 16, we need those two numbers. Okay. So let's go ahead and bring up C3H7CO2 minus. I'm writing the equation down again, just so that we can do our little calculation. Okay, the weak base is going to react with water. The water will donate the H plus, transfer an H plus to it. I'm going to put the H in the front, so it is like they gave it to you. And you'll say, hey, wait a minute, that's butanoic acid. But yeah, that's right, that's right. But you also get hydroxide. And the hydroxide is going to make the solution basic. We know this is 0.1313 molar. So now KB is what? I'm just going through one of these problems from chapter 16. You can review that. Products overreacted. HC3H7CO2, concentration. OH minus, concentration. C3. C3H7 CO2 minus. That KB is 6.607 times 10 to the minus 10, right? Okay, so there's a whole second reaction here that we have to deal with. The first reaction was the titration between the butanoic acid and potassium hydroxide. But that left us with none of the reactants, but with a weak base. Now that weak base is going to react with water to form a conjugate acid and hydroxide, hydroxide is what's going to determine the pH. Okay. So how do we deal with that? Well, we do an ice table again, right? You take the reaction. Sorry. Remember, it's reversible, right? Because it's a weak base. Okay, I'm just writing that equation again. 0.1313 molar. Don't worry about the water. The water is a liquid. It's not involved in equilibrium. These are 0. Q is less than K, so the reaction shifts to the right. You lose X on this side, you gain X on this side. At equilibrium, you're going to have 0.1313 minus X, X and X. Here's the expression for the equilibrium constant. We can substitute these X's in and the 0.1313 minus X. Those can get substituted right back in. So KB would be X times X, which is X squared. Hopefully it's familiar to you, over 0.1313 minus X. Okay. Just a standard equilibrium problem. Now, since KB is small, that means X is going to be very small as well, probably 10 to the minus 5. If it's that small, that means we can neglect it in the denominator. 0.1313 minus a very small number is going to be approximately 0.1313. So now we can say that X squared over 0.1313 is approximately equal to 6.607. Certainly will be within 5% for this one. And now what am I going to do? I'm going to solve for X because X is the hydroxide concentration at equilibrium. If I can get that, I can find the pOH. So solve for X. Well, let's go through the algebra. X squared would be 0.1313 times 6.607 times 10 to the minus 10. And then X would be the square root of that. Okay, so when you go through that, it looks like you get 9.316 times 10 to the minus 6. So I multiplied the two numbers together and then took the square root. So now, since X is the concentration of hydroxide, I can now find the pOH. It's just the minus, it's just the negative log of that number. Okay, and when you do the negative log of that, you get 5.03. And so then the last step, pH is 14 minus pOH. So that would be 14 minus 5.03, and you get 8.97, which kind of makes sense because it's a weak base. So if you have a weak base, your pH is going to be above 7, but not that much above 7, not 11 or 12, because 11 or 12 is generally what you get when you have a strong base. This is a weak base. It's not a very strong base at all. Okay? So keep in mind that particular problem, you might want to watch the video more than once. There's 2 full-on steps in this. One is the titration, reacting the acid and the base to figure out what's left over. The second part is now that what's left over happens to be a weak base, you treat that weak base as your reactant with water to figure out what you're going to be left with. And then you calculate the pH of that particular solution. Okay? So that's a pretty standard calculation in chemistry textbooks. Make sure you practice that one and get it down.